Okay, good evening. Welcome to section 2.1 of Geometry Revisited. This is the first section in a chapter about circles, and this section is called The Power of a Point with Respect to a Circle. So we're going to learn a new definition, something that I think you don't usually see in a geometry book, called the power of a point. And so we're going to start actually in a very similar way to chapter 1 started. We're going to start with a similar, or a theorem we probably all remember from our original geometry classes. And then we're going to ask a fairly natural question. So, this theorem goes all the way back to Euclid. So this theorem has been known for a long time. When you have two intersecting chords in a circle, AP times PA prime equals BP times BP prime. And this theorem is actually not too difficult to prove. In fact, I'm going to not prove it. But I'll just remind you that you can prove it by taking a look at the circle ABP and B prime PA prime. And you'll find a bunch of angles in there that are the same. For example, BAA prime, this angle here, is equal to this angle here, B prime A, because they cut off the same arc in a circle. You'll find those triangles are similar, and then you look at the ratios of the sides and the theorem falls out. But we're not going to, don't want to focus too much on this, but we do want to ask the same question that we asked in section 1.1. If these two things are equal to each other, are they equal to something interesting? What are they equal to? And the book gives a very clever little proof. The book says, well, we'll take this theorem of Euclid, and we'll draw put down the red marker and grab a different red marker. We'll draw something that I'll call CPC prime, and this is the diameter of the circle. So any two chords that cut through here are going to satisfy this. So we know that AP times PA prime equals CP times PC prime. But this is the diameter of the circle, so here's the center O, here's the radius R, and this P is going to be a distance little d, and this line up here is going to be distance R minus d. So CP is R minus d, the radius of the circle minus d. PC1 is equal to R plus d. So now, let me go back to a darker color so you can see. So we know that AP times PA prime from Euclid equals CP times P, I should have called it C prime, sorry. And this happens to equal R minus d, little d, times R plus d. And so all these things are equal to R squared minus d squared. So in other words, when you multiply the lengths of the segments of how the chords are split, you get an interesting number, which is the radius of the circle squared minus d squared, where d is the distance from the point P to the center of the circle. Not too hard to prove. I want to draw two other pictures from this section before we move on to a really cool theorem, so hold for just 1 second. Okay, here's the second picture, and this just is to show what happens if the point P is outside of the circle. The same theorem of Euclid holds that PA times PA prime equals PB times PB prime. And if we draw a line segment from P through the center of the circle, and that P is a distance d from the center, we get PC equals times PC prime is equal to this, and PC is equal to the distance minus 1 radius, so we'll call that d minus r, times the distance plus the radius, d plus r. So if P is outside of the circle, we get that this multiplication multiplies to d squared minus r squared. So you see a very similar theorem holds. If it's inside the circle, it's r squared minus d squared, and if it's outside the circle, it's d squared minus r squared. And this quantity, d squared minus r squared, is called the power of a point with respect to the circle. So if it's inside the circle, this multiplication gives the negative of the power. If the point is outside the circle, it gives the positive value of the power. And this is just a nice little definition. One of the exercises asks you to take a look at what d squared minus r squared represents geometrically, and that's actually an interesting exercise. And I'll let you take a look at that for yourself. Okay, one last quick thing now that we've introduced this very simple concept of the power of a point, being the distance squared away from the center less the radius squared. I want to show one nice little theorem that they prove. Unfortunately, I don't have enough time to step through the proof. That's a kind of a neat thing, and again, if you get the book yourself, you'll be able to follow this. It's not complicated at all, and actually it's very clever. I wish I had more time. Hold for just a second. Okay, and here's the last little theorem from this section, which is very fascinating. And again, the proof's actually very clever. I don't have time to walk all the way through it, but here's the theorem. It's due to Euler. The distance from the circumcenter to the incenter of a triangle, which we'll call d, has the property that d squared equals big R squared minus 2RR. So the distance squared equals the circumradius squared minus twice the inradius times the circumradius. Very clever little formula. In my picture, here you see our triangle ABC. I've drawn the circumcenter O. I've drawn the incenter D. And you remember that the incenter, get a different color marker, you'll remember that the incenter is the intersection of the angle bisectors. So I've drawn one angle bisector A, extending it through and hitting here at L, which I'll get to in a minute. But I have an angle alpha there and an angle alpha here. Those are equal by definition. I have an angle bisector here, B running through here and hitting D. Those have, we'll call those, following the convention in the book, beta, beta. One interesting observation is that this line here, B to C, and then C extending down to L, cuts off the same arc LC as this angle, LAC. So that means that angle is the same. This diameter that I've drawn, L going through O up to this point M, cuts off this arc BL. When I look at LMB, while also LAB cuts that off, so that means this angle is alpha up here too. And so you chase through a couple angles, you find some similar triangles, and then a very clever application of the theorem due to Euclid that we looked at in the first section, and our little distance d falls out of the formula. So it's a clever little proof, and it implies a few constraints on the circumradius and the inradius. One of the problems in the book asks you to prove that the circumradius is at least twice as large as the inradius, which you can see from that formula. It's a neat little example. As I said, I wish I had a little bit more time to go through the proof in detail, but I would encourage you to go through the book, get the book and go through this proof. It's only about half a page. Very clever argument. Okay, well, thanks for watching. On to section 2.2 tomorrow.